I'm gonna scroll past this, so I apologize in advance if you weren't done typing, but you can always come back and watch it again. Just for the sake of time. For data set number 3, a study was conducted to evaluate the effect of varying external loads on power output in males and females while running up 3 flights of stairs. 20 participants, 10 male and 10 female, performed the task under 5 different conditions. So no external load, adding 5% of their body weight, adding 10%, 15, and 20% of their body weight. And then we measured power output normalized by their body weight or body mass. Okay, so it's reported as watts per kilogram. So that's what's shown in our data here, where each of these values represents their power output. And then I've organized, this is the chunk for females, this is the chunk for males. If we were to organize this as, I don't know, words are hard. If we organize it to go into SPSS, because we have, and I'm giving away answers now, because we have between subject variable males and females, right? We would need to have a value for both males and females, right? Maybe we say 1 is females and 2 is males, just because that's the order they're listed in. We would need a column that specifies which gender each value is identified with. And then pretty much we could just copy our data over, right? And say, oh, well, these belong to our female participants. Sorry for the scrolling. And then this set of data would represent our male participants who have a data label of 2. And then when we put this into SPSS, this chunk, we would just have to make sure that this variable is identified as nominal. The rest of these would be identified as scale variables because of the values that are in each column. They're actually representing something that we measured, right? But when we have a between subject factor, we need data labels like this. When we have a within subject factor, each level of that within subject factor gets its own column. Okay. So with that being said, kind of gave away some answers here, so I'll just type them in. Our independent variables, we have 2. Okay, so gender being one of them, or sex. I use them interchangeably in this class, even though they technically are not the same thing, but it's easier for grading anyways. That's a different story. This is a nominal variable, has 2 levels, and gender would be our between subject factor because males cannot be measured at the same time that females are, so they're mutually exclusive groups, 2 separate groups, right? And then our loading condition, I think in the output I just put this as load, right? But it's how much weight we are adding to the task of running up the stairs. That would also be considered nominal because, again, different categories. We have 5 levels, but each subject does each of these, right? Because we've got 5, end up with 5 measurements for each person, or each row is a subject. So this is a within subject variable. Okay. Our dependent variable would end up being the power output. And that would be ratio. What type of ANOVA would I want to run for this one? Yeah. So we could label this a couple of ways. Juan suggested if we were using like a level by level naming convention, we could say it's a 2x5 mixed ANOVA. You could say it's a two-way mixed ANOVA, a 2x5 between within. I'm going to type it that way just so we have an example of it written that way. If you wrote a 5x2 between within, that would be incorrect. Okay. Reason being is that the order of the levels has to be the same as the between within order. So 2x5 between within would be the way you would write it if we use this naming convention. But any of the ones I already mentioned would be fine. Again, I'm just going to put the assumptions that we test in SPSS, but we have all of the good study design, random sampling, normal distribution stuff that go along with a two-way mixed ANOVA. Red. So one of our assumptions in SPSS is going to be for the between subject factor. One is going to be for the within subject factor. What are they? Hodges and Levine's test. Yeah. So between subject factor, we're going to look at homogeneity of variance. The within subject factor, we're going to look at sphericity or Machli's test. Okay. Also take note for the interaction. The interaction gets posted in the within subject factor ANOVA table. So whatever we decide to do with our loading condition is what we end up deciding to use for our main effect of our interaction. Okay. So for our p-values, we're going to have a p-value for homogeneity of variance. So I'll type that out now. We're also going to have ones for sphericity. Whee. Data set number 3. Okay. So for this one, I did analyze repeated measures or general linear model repeated measures. I inserted for my within subject factor, I called it load, and I said there were 5 levels. So I've already like transferred what like no load, 5%, 10%, 15, 20% in the tables below, or below this, like pairwise comparison specifically. But remember to go back and look at how you organize your data when you run the test yourself. Because for the within subject factors, it'll always put the number or the number level that it's associated with when you set up the test. For gender, 1 is females, 2 is males, just as a good reference. The first thing I'm going to look at, I'm going to go in order of the actual output, but we have Machli's test of sphericity. That's kind of the first thing pops up here. And we have a p-value of 0.163 for our load condition. So we would report that because this is greater than 0.05, we accept the null hypothesis and say that the variances of the differences between loading conditions are relatively equal. And because we accept sphericity with our within subject factor, we're also going to say we accept sphericity or assume sphericity for our interaction effect. So I'm going to skip down where we're going to have a p-value for gender, we'll have a p-value for load, and then we'll also have a p-value for gender and load. Okay. Because we met sphericity, the loading condition, we see we have a p-value of 0.0 or less than 0.001. And then our interaction effect, load and gender, we have also a p-value less than 0.001. So p less than 0.001 is less than 0.05. This would tell us we reject the null. So in that respect, there is at least one significant difference between loading conditions for power output. There's a lot of ways you could write the main effect. You could say the type of loading condition has a significant effect on power output. That's probably the next easiest one to write. And then our interaction effect had a p-value less than 0.001. So we'd also reject the null hypothesis for that one and say there is a significant interaction effect between gender and load for power output. I think most everybody started doing better on this on the, what was it, activity 8. But using the wording like that significant interaction effect between both independent variables, that's kind of a specific wording. I think there were some people who still weren't writing it that way, where they were saying like, oh, there's a significant effect of gender and load on power output, which is not what the interaction effect looks at, but that would be for those ones. Questions so far? All right. So if we keep moving down our thing, and if you did have a question, you can still type it in. I'll just keep moving on so I don't have to edit out large pauses. We were in the tested within subjects effects table. Now we can scroll down to Levine's test for our homogeneity variance. And remember, in a mixed ANOVA, you're going to end up with a p-value for each of the levels of the within subject independent variable. And this is just saying we're looking at, are the variances equal between males and females when we just look at the no weight condition, when we just look at the 5%, 10%, 15, 20% conditions alone. So you should have 5 p-values to report for each of those. Let's say, we could write it this way. There are, hey, I want it red. There are equal variances between genders for our no load condition, which is the first one. So that would be p is equal to 0.663. The next p-value will be for the 5% load, which is equal to 656 or 0.656. Next one is 10%. That's 0.675. For the 15% or added 15% load condition, that one's less than 0.05, so I'm going to save that. And then my last condition that met my homogeneity of variance is the plus 20% condition, which had a p-value equal to 0.261. Okay. I would also want to note that equal variances were not met for the plus 15% condition. So there are not equal variances between genders for the there it is, 15% condition, and that had a p-value equal to 0.008. Now, even though this is a violation, I think I told you guys before, two-way or like the univariate, or not univariate, repeated measures and univariate tests don't have the option to add a Welch's test when you violate homogeneity of variance. So for the most part, like the ANOVAs that we run, or the actual calculations that are run in SPSS, the test should be robust enough to kind of counteract the violation. So usually if you have a majority of your variables that have met your assumption, it's okay to like proceed. But it's kind of like a proceed with caution. So even though we violated homogeneity of variance for this plus 15% condition, we're still going to read the ANOVA table as if we met the assumption for all of the levels of our between subject variable within all of the levels of our within subject variable. So we shall say for now, we've met all of our assumptions. So then we can look at our p-value in our test of between subjects effects table. And that will tell us what our p-value is for the main effect of gender. So here we could see a p-value less than 0.001. Which is less than 0.05. So we'd reject the null and say that gender has a significant effect on power output. So based on those p-values, which pairwise comparisons are we interested in looking at? All of them, yeah. So I'll put in gender. We'll have pairwise comparisons for load. And then we'll have one set of pairwise comparisons for the interaction effect, where we're looking at differences between genders within each loading condition. And then we'll have another one that looks at differences between loading conditions within each gender. What am I typing? Within. There we go. Okay. So pairwise comparisons for gender is listed first. And again, it should be redundant with our ANOVA table because there's only 2 levels for gender. So this just indicates that, oh, just kidding. Hold on a second. This would just indicate that males have a significantly different power output than females, regardless of the loading condition. And I just realized I forgot to put the regardless part up here. I'm not going to dock you points if you don't put it. I haven't been on your activities, but it's just a good thing to note. So I'll add that really quick. And if somebody, oh wait, no, you don't have access to it. Just kidding. Bad question. It'll stay in my head. We won't release that one. Okay. This second main effect for load would be regardless of gender. Okay. So that takes care of one set of pairwise comparisons. Pairwise comparisons for our loading conditions. I've already highlighted the significant ones, which are basically all of the conditions in comparison to the no load condition. But if we were to look at comparing, like 5% to 10% or 10% to 20%, those ones don't come out as significantly different. So the way that we could write this is that this is with the no load condition. So let's say the not bolded, there we go. The no load condition was significantly different from all other loading conditions. That makes sense. Okay, and again, this would be regardless of gender. Oh, just kidding. Our next set of pairs would be kind of in this number 3, pairwise comparisons. So this is looking at differences between genders within each loading condition. And we can see from our p-values that all of the pairs are significant. So a way that we could write this is that males had significantly different power output compared to females for all loading conditions. While we're down here, I'll just go ahead and do the effect size so that we don't have to skip back to it. But because we had a significant difference in each loading condition, we would report the effect sizes within each loading condition. So I've kind of skipped to number 24, gender within load. And we can say there are large effect sizes for the differences between males and females in the no load, plus 5%, plus 10%, 15%, and 20% conditions. And then within each of these, I would just fill in the effect sizes, right? So I've got a 0.976, a 0.980, 0.973, 0.980, and 0.968. Okay. The other set of pairwise comparisons is going to be looking at significant differences between our loading conditions within genders. And again, if I'm going too fast, you can always come back to the recording just to double check to make sure you got everything. And here we could see within the females, no load was significantly different from the 5%, and 5% was significantly different from 15%. So just two pairs. The way that Juan had mentioned you could list stuff before was we could say like within females, there were significant differences between, and then we can create a list. We could say no load and plus 5%, and then 5% and what was it, 15? Plus 15? Yeah. That would be an acceptable answer. Okay. And I think you can use bullet lists or make bullet lists in like written response questions. So that should work. Within males, there were significant differences between, let's see. We have differences between no load and 10%, 15%, and 20%, and then a difference between 5 and 15%. So you could say no load and 10%, no load and 15%, no load and 20%, and then 5% and 15. Okay, so these four pairs are these four highlighted cells in here. Okay, since we have significant pairs within both male and female groupings, in our multivariate test, when we report the effect sizes, hold on a second. I think I have a page break here. I'm going to push it downwards. So within females, I'm going to kind of like abbreviate or expedite some of these processes here. Within females, our effect size was 0.605, which is considered large. And within our males, the effect size was 0.856, also considered large. Question is, for mixed ANOVAs, the effect size for interaction only needs to have one value that was significant to be mentioned. Yes, but that's also true for any two-way ANOVA. So that just tells us, because there are different combinations of interactions, that's why we don't report the singular effect size in the main ANOVA table, because it doesn't end up giving us a full picture of the size. Yeah, so it all for all two ways. But it'll be different in your like if you have a two-way independent versus a two-way mix versus a two-way repeated measures, the table that's underneath will vary whether it says multivariate or univariate. So if you're looking at differences between a within subject factor, it'll come out as a multivariate test. If you're looking at differences between a between subject factor, it comes out as a univariate test, which is what is on this one here. But in either case, interaction effect sizes are going to be in the table underneath the pairwise comparisons. So just make sure you visit both. Okay, so I think the last thing in this example that we have is to report the effect sizes for gender and load. And those are both going to be in our ANOVA tables, respectively. So my effect size for load is 0.3. Whoops, 0.3. That would be considered large. And then my effect size for gender, because gender is my between subject factor, it's going to be in my between subject factor ANOVA table. So that one would be 0.997, which is also considered a large effect size. Well, okay. Questions on anything in that one? Okay. Back up to the effect size for the within subject, please. So the within subject factor was load, and its effect size is listed next to its p-value in the ANOVA table. So it should be 0.3. It'll probably be varied, to be honest. And I might not even ask you to report every single effect size just to cut down on time, because I know these kind of take a while. So it would be, it might be something like, what's the effect size for differences between loads within females? And then you'd say, okay, well, where's the effect size for the differences between loads within females? You decide, oh, it's like this one. And then we have significant effects with females, right? So differences between loads within females would end up being that effect size. Yeah, the interactions for the mixed ones do take a while because there's so many. But that might be one way I would phrase it. So then you're not like having to type out every single one. It's just like, what is the question asking for? And then you find it in the output. And then you're only reporting like one or two effect sizes and interpreting one or two effect sizes instead of interpreting all of them. For the pairs, I probably would list like every possible pair and do like a multi-select type question where you then just select all of the pairs that were significant instead of having to type them out, because again, it saves on time. And I would probably like separate them by the main effect. So if anything, you just have to pay attention to that. So I would say like what are the significant pairs, if any, between genders within the loading conditions? And then I would have like males versus females within no load, within plus 5%, within plus 10%. And then you would just check the boxes. And then I think for those ones, I usually set them up as correct choices. So if you select the correct ones and the incorrect ones are not selected, then that gives you the full point. So if that it ends up being like if you made a wrong choice and like you selected a pair that was significant that wasn't, it actually counts against you. But that's how those are calculated. So there's like a lot of partial credit in those questions based on what you would choose. But that's probably how I would do those ones. And the effect sizes. The regular like main effect p-values and interpretations will probably be the same as what they've been for your activities, where you have to write those ones out. But those ones don't take as long. So or writing them out doesn't take as long as like listing every pair and effect size. So I probably will keep those pretty similar to what you had for the last exam. Okay. For data set number 4, I know we're starting to run short on time, which I kind of had an idea would happen. So I'm just going to do the variables for these ones and the type of ANOVA, just so you make sure you've got that part down. I feel like that's kind of like the first battle you have to get through. And because you guys have the correct outputs, I'll just let you refer to those for what the p-values are. All of them are highlighted already, so you don't have to worry about picking the wrong one as long as you type the highlighted p-value that's associated with the question being asked on the little review quiz, you're fine. So this research scenario, it says we have a study was conducted to evaluate the differences in heart rate and beats per minute during the aiming process of archery among different levels of experience, as well as different bow types used for shooting. We have 135 archers, 45 beginner, 45 intermediate, and 45 advanced that were recruited to participate. Subjects in each experience level were equally divided and randomly assigned to one of 3 bow types. So in this case, we have bare bow, recurve, and compound. And then after a 1-week familiarization period, each subject's heart rate was averaged over 10 trials while they were aiming at a target at a fixed distance. And then heart rate in our spreadsheet is reported as a percent of their heart rate max. So in this instance, we can see we've got 3 separate experience levels. I feel like that one is a fairly dead giveaway. It's a between subject factor. So we'll say experience is one of our independent variables is nominal data. It has 3 levels, right? Beginner, intermediate, advanced. And it's a between subject factor because each person is different or has a different group that they've been assigned to. Our other independent variable is going to be the type of bow that was used. Also nominal because they're in categories. And this one also has 3 levels and is also a between subject factor. The key in the research scenario is that people were equally divided and randomly assigned to one of 3 bow types. So when we organize this one in Excel, we would need a legend for our between subject variables, right? These would be our experience levels, so beginner, intermediate, advanced. And then maybe we have another set of labels for our different like our different bow types. So then when you set this up, you would have experience in one column, or like the labels for that experience level. You would have a column for the type of bow somebody used, and then you would have the heart rate for the dependent variable that was measured. So you could go through this step by step and say, all right, this chunk of people were beginners, so they get a data label of 1 under experience. And this was copied from the bare bow bow type, also data label of 1. Okay. And then you would just keep copying and pasting and then stacking your data until you have everybody's like possible label combination figured out. Okay. Oh, I already gave it away, but dependent variable was heart rate, which would be considered ratio data. And based on this information, most of you have probably deduced that this would be a two-way independent ANOVA. So in our output, we would want to check our assumption first. Right, so we have Levine's test, and 0.488 is larger than 0.05, so that tells us to accept the null hypothesis. We've met our assumption for homogeneity of variance. And then our test of between subjects effects table gives us the p-values for our main effect of experience, which is not significant. Our main effect for the bow type, which is significant, and the interaction effect between experience and bow type, which is also significant. So in my copy, I deleted the pairwise comparisons for experience because it wasn't significant, so we don't need to look at those post hoc tests. But similar to our previous examples, you would then go in to your pairwise comparisons, note which pairs are different from each other for both bow type, as well as looking at differences between experience levels within each bow type and differences between bow types within each experience level. And then similar to our other two-way ANOVA examples, you would then consult, like if we have significant differences or significant pairs within our compound grouping, then you would report the effect size underneath that table for just the compound group. For our other one, our other set of pairwise comparisons, for the interaction, we were looking at differences between bow types within experience level. We had a significant pair within the beginner level, as well as a significant pair in the advanced level. So that's why I've only highlighted 2 effect sizes in my univariate table underneath. Okay. But the process of how we approach this is the same as the previous like two-way ANOVA examples. So figure out if you have, if you've met your assumptions, if you have significant main effects. For the significant main effects, you look at pairwise comparisons or post hoc tests. And then for the significant interaction pairs and main effect pairs, you report the effect sizes. But again, if you look at my copy, you're guaranteed to have the answers that are in the the review quiz. And I don't remember if I actually asked to report. I think this one I asked to report a p-value. But this is posted, so. Just to wrap up, we'll do the same thing we just did for the last one on our final data set. So a study was conducted to evaluate the effects that different types of squats have on range of motion at the knee. There were 12 subjects who were asked to perform 5 repetitions for each of the following: a front squat, a back squat, and an overhead squat. And the weight lifted was set to 80% of a 1 rep max for each condition. 1RM values were determined on 3 separate lifting days just to account for fatigue. And then each squat position was tested in random order and spaced 2 days apart, again to eliminate potential effects of fatigue. So knee range of motion was defined as the maximum angular displacement of the lower leg from the upright start position and was averaged over 5 trials. So data-wise, we've got 12 subjects who each did one of the types of squats. And then these values are the average knee range of motion. Okay. So based on that information, the type of squat is our independent variable. It's nominal with 3 levels. And it would be considered a within subject factor because everybody underwent each condition. The way the data are organized right now, you could literally just copy and paste into SPSS. So this one doesn't require any rearranging. Our dependent variable was knee range of motion. This one I would say is ratio because generally speaking, in normal people, the knee only goes through like 180 degrees, if that, right? Sometimes a little bit more if someone has hyperextension, but your value shouldn't be both positive and negative. So in that respect, it'd be ratio. We have had range of motion examples where it was interval. So if I gave you a range of motion question on the exam and you put interval, I would probably still count it as right because of the examples we've had previously. But given that we have one within subject independent variable and a single parametric dependent variable, this is the only ANOVA we haven't done in the review yet. It's a one-way repeated measures ANOVA. So for our statistical test results, we would need to see if we've met the assumption for sphericity and then figure out what the p-value of the main effect is based on if sphericity is assumed or not. If we have a significant effect for our type of squat, we would look at pairwise comparisons. And then for our effect size, we would report omega squared, which has to be calculated. And I think this one, I did want to point out something on this one, so just that people aren't confused. So this one actually violated sphericity because we have a p-value less than 0.05 in Moduley's test, which means look at the greenhouse geyser value. This was less than or equal to 0.75. So I used a greenhouse geyser adjustment. Interesting thing that happened, and it's not uncommon, especially when you have a violation of sphericity. If the adjustment factor to degrees of freedom, sometimes it messes with how your significance is figured out in the pairwise comparison. So this ended up giving us a p-value of 0.045 for the main effect of squat, which is indicating that there is at least one significant difference between the types of squats for knee range of motion. But when I go to the pairwise comparisons for the differences to see like where the differences are, there didn't end up being any significant pairs. And I don't exactly know why this always happens. I do know it's a calculation thing, like kind of in the background in SPSS, and it has to do with something with the adjustment. But because like 0.045 is kind of close to 0.5, that's why I'm guessing we didn't end up with any significant pairs, but it's not unheard of, but it's not super common that this always happens. But for the answers, like if you're writing these out, you could say like there was a significant effect of squat, but the pairwise comparisons didn't show any significant pairs, and then just leave it at that. I don't think this will happen to you on your exam, so it's not something you should be super worried about, but it is something I wanted to mention before I release you into the wild and say, take this quiz. I don't even think I asked that question on the quiz just because I figured answers would kind of be variable, but just so you know, that might eliminate some questions that I get from people through email. The last two examples on here are from are for calculating the different components of your ANOVA tables. So I've given you a research scenario. From those, you want to figure out, like say for within or a independent ANOVA, you need to know how many groups there are in your total sample size. And once you figure those parts out, you can figure out your degrees of freedom. And then that pretty much sets you up to calculate the rest of your table. Similar thing goes with the repeated measures ANOVA table, where you want to figure out how many groups you have, how many subjects you have total, and then how many total data points there are, which would be basically taking the number of subjects you have, multiply it by the number of groups you have. Then with that information, you should be able to figure out degrees of freedom, mean square, F statistics, etc. All of the calculations of these are the appropriate formulas. I did put those in the study guide if you want like a quick reference, like one place you can get everything. They're also in the independent ANOVA would be in the module 7 lecture part 1, and the one-way repeated measures ANOVA table template is in module 8 part 1 PowerPoint. So you can always jump back to those if that's helpful for you. All right, so that's pretty much what I had planned for today. I can go back, since I didn't do all of data set 4 and 5, I can just record a separate video if you want to watch going through that and then seeing examples of how I would phrase stuff. But just know those probably wouldn't be posted until like later tonight / tomorrow, depending on if YouTube cooperates today. But I can post those for you guys to reference if you want them. Does anyone have any other questions on like what to expect on the exam or just in general? Final project questions? Anything class related?